Now we're going to start talking about sorting algorithms. Sorting has been a foundational problem for the analysis of algorithms, and hundreds of different sorting algorithms have been developed. Knuth's Art of Computer Programming has nearly 400 pages devoted to sorting algorithms. In this course, though, we're just going to discuss 6 sorting algorithms. And these are insertion sort, merge sort, quick sort, heap sort, and 2 which are slightly different, counting sort and radix sort. Okay, so we're going to start off with insertion sort. Insertion sort has worst case complexity theta of n squared, which is not very good as far as sorting algorithms go, but it is very straightforward to implement and it has many nice properties. And this is going to lead us into a general discussion about what kind of properties we would like a sorting algorithm to have. So we're going to start off with insertion sort. You've probably already used insertion sort. This is often how you sort playing cards in your hand. You have cards in your hand which are already sorted. When you pick up a new card, then you insert that card in its proper position so that the cards in your hand remain sorted. Let's see how we can do this in an algorithm. So imagine that we have an array which is sorted except for the last element. Okay, so the 2 and the last position of this array is not where it should be. And we want to insert this element into its proper position. So how can we do that? Well, as long as 2 is smaller than the element before it, we just swap these elements. Okay, so we compare 2 with the element before it. The element before it is 8. 2 is less than 8, so we swap them. Now again, we compare 2 with the element before it. The element before it is 7. 2 is less than 7, so we swap them. Again, now we compare 2 with 5. 2 is less than 5, so we swap them. Next, we compare 2 with 3. 2 is less than 3, so we swap them. Okay, now we compare 2 with the element before it. The element before it is now 2, and 2 is not less than 2. Then the algorithm stops, and we're done. So there's a subtle point here that I want to emphasize. The rule that we chose was that we only swap an element with its left neighbor if it is strictly less than this neighbor. We would still get a sorted array if we changed this rule to instead swap an element with its left neighbor as long as it's less than or equal to its neighbor, right? So in this case, we could swap the 2 with the 2 to the left of it and still have a sorted array. But there's a good reason to choose the rule to only swap if the element is strictly less than its left neighbor. And we're going to discuss this more later. For now, just note that with this rule that you only swap if you're strictly less than your left neighbor, the 2 that started in the last position of the array began to the right of the other 2, and it remains to the right when this algorithm ends. So in other words, for elements that are equal, the tie is broken by their original position in the array. So this is an important property for a sorting algorithm. In an algorithm which has this property, that ties are broken by the position of the elements in the original array. Sorting algorithms with that property are called stable sorting algorithms, and we're going to discuss this more later. So let's look at code for what we've just done. The input to this function is a vector, vec, and an index I. We're going to assume that the elements 0 through I minus 1 in the vector are already in sorted order. And we wish to move the last element, vec of I, into the correct position so that elements 0 through I of the vector become sorted. So we have a simple loop here to keep swapping the element with its left neighbor so long as there is a left neighbor and the element is smaller than its left neighbor. Okay, I'm just using a library function here, standard swap, to do the swap. Let's look at the memory used by this program. Apart from the original vector, we just have the index variable I, and behind the scenes when we do the swap operation, we need to use a temporary variable to hold an int while we do the swap. An algorithm that just uses a constant number of extra variables to hold indices and elements, in addition to the memory for the original input vector, is called in-place. So this algorithm here is an in-place algorithm. Whether or not a sorting algorithm is in place is another important property to look for. Now let us look at how much time this algorithm takes in the worst case. The worst case is when the element to be inserted has to travel the farthest. That is, when it is smaller than all the other elements in the array, and so it has to move to the very beginning of the array. In this case, when the sorted portion of the array has size I, we have to do I comparisons and I swaps. Each comparison and swap takes constant time, so the worst case running time is theta of I. So with this building block of inserting the last element of an otherwise sorted array into place, it's easy to finish the insertion sort algorithm. An array of size 1 is always sorted, so that's our starting point. We can thus use the insert1 function to put the second element of the array in its correct position with respect to the first element. After we do that, then the first two elements are already in sorted order. So then we can use the insert1 function to put the third element in its correct place. Then the first three elements are in sorted order. And we can use insert1 to put the fourth element in place. We keep doing this for I equals 1 to n minus 1 when the array has size n. And after that, the entire array will be sorted. Let's see a little bit more formally why this algorithm is correct. This will let us introduce a very important notion for reasoning about algorithms, which is the notion of an invariant. An invariant is something that stays true throughout an algorithm. I claim that an invariant in insertion sort is that at the start of the ith iteration of the for loop, vec 0 through vec I minus 1 are in sorted order. Let's see why this invariant is true. The technique that we're going to use is a general one that you will often see. We first show that the invariant is true at the beginning of the algorithm. This is the initialization step. In this case, at the start of the first iteration of the for loop, the invariant says that vec of 0, that is the first element of the vector, is sorted. And that's true. Any vector of a single element is sorted. Now that we've shown that the invariant holds at the start of the algorithm, we want to show what's called maintenance. If the invariant is true at the start of the ith iteration, then it will also hold at the start of the I plus first iteration. In this case, if the invariant holds at the start of the ith iteration, then vec 0 through vec I minus 1 are in sorted order when we call insert1 with arguments vec and I. That vec 0 up to vec I minus 1 are in sorted order is exactly the assumption needed by insert1 in order to insert vec of I into its correct place. Thus, since the assumption needed by insert1 holds, vec of I will be inserted into its correct place, and then vec of 0 through vec of I will be in sorted order. This exactly says that the invariant holds at the start of the I plus first iteration. By showing that the invariant holds at the start of the algorithm and showing maintenance, that if it holds at the start of the ith iteration, then it also holds at the start of the I plus first iteration, together these mean that the invariant holds throughout the algorithm. This is just like a proof by induction, if you've seen that before. Now let's see what the invariant holding at the end of the algorithm tells us. That is the termination condition. The loop terminates when I is equal to the size of the vector. At this point, the invariant tells us that vec of 0 through the last element of the array is sorted. And that's exactly what we want to show that the algorithm is a correct sorting algorithm. We have already argued that the building block insert 1, which correctly puts the last element into sorted position in an otherwise sorted vector of size I, takes time theta of I. In insertion sort, we just call insert 1 for I equals 1 up to n minus 1. So the running time is a constant times the sum of I from I equals 1 to n minus 1. This is the same sum we saw in the analysis of the double for loop algorithm for a contains duplicate. So we know that this is n times n minus 1 divided by 2. This tells us that the running time of insertion sort is order n squared. For any input, it's going to run at most a constant times n squared steps. What about our lower bound? Is there an input which makes insertion sort take a constant times n squared steps? Let's go back to the building block of insert 1. Remember that the worst case for insert 1 is when the element being inserted is smaller than all the previous elements in the array. Can we design an input where insert 1 is always realizing this worst case behavior? Indeed we can, if the original input is sorted in decreasing order. Then whenever we call insert 1, the element being inserted has to go all the way to the front of the array. In this case, insertion sort really will take omega of n squared steps. Thus we can say that the worst case running time of insertion sort is theta of n squared. Again, what that means is that for every input, it will always run at most a constant times n squared steps. And there also exists an input which makes the algorithm take a constant times n squared steps. We can also look at the best case complexity of insertion sort. The algorithm will always take at least n minus 1 steps, because we have the outer for loop, which goes from I equals 1 to n minus 1. If the original array is sorted, then the algorithm will just take order of n steps. In this case, each time we call insert 1, then we just do one comparison and no swaps, as the element to be inserted is already in the right place. So we can say that the best case running time of insertion sort is theta of n. There exists an input where insertion sort only takes a constant times n steps, and for every input, insertion sort will always take at least a constant times n steps.